on the right, that is inaccurate. So like, don't be that worried about it. Um, okay, so I'm going to talk about diagrams of immersed surfaces, and immersed is in parentheses because you can't really understand the immersed surfaces until you know how to draw embedded surfaces. So we'll just like see how far we go. This is joint with Mark Hughes, who's a professor at Brigham Young, and Sungwa Kim, who's a postdoc at the Institute for Basic Science in Korea. So there's just like 24-hour time zones of like conversation, which is very fun. Okay, so I'm telling you about surfaces smoothly embedded or immersed in four manifolds, which if you don't usually think about these things, so if you're not Jason, then you should think of this as an analog of knot theory, which is probably more familiar. So maybe we all know that knots are circles smoothly embedded in a three manifold, and maybe you're like really pedantic and you're like, is it the embedding or is it the image of the embedding? But that's like, it's kind of dumb. But knotted surfaces are just everything one dimension up. You have a surface that is smoothly embedded in a four manifold. And so even ignoring how bad four-dimensional topology is, you can see that there's already an extra level of complexity where there's only one, compact connected closed one manifold circle. But when you consider surfaces, you could mean like just two spheres, or maybe you allow them to be positive genus, or maybe you allow them to be non-orientable. And there's just like a whole, extra family of bad things that can happen. Okay, so why would you be interested in surfaces in four manifolds? For a lot of the same reasons you might be interested in knots. So I guess I should explain why you might be interested in knots, because a lot of people aren't, but I think they're fine. You can use knots in particular to describe any three manifold you want. Then you have to believe me that three manifolds are interesting, but I feel like we're sort of all on the same page with this one. But it's a famous theorem of Licorice and Wallace that any three manifold can be obtained by doing surgery on some list of knots in S3. So starting from S3. It's actually a theorem of Iwase. So this is a certain surgery operation that any four manifold can be obtained by starting from something simple, not exactly S4, but something with a name, and doing surgery on some family of tori. So we can like have an analog of Dane surgery and a Dane surgery theorem in dimension 4. If instead of surgery you like branched covers, maybe you know that every three manifold is a branched cover over S3, branched over some knot. It turns out that every four manifold is a branched cover over S4, branched over some immersed surface. So you can also use them as coverings to describe four manifolds. I'm not writing that much because this isn't that important. I'm just like hyping you up. You can also use knots and knotted surfaces to find exotic behavior, where if you haven't heard that term before, exotic means the difference between the smooth and the not smooth category in dimension 4. If we're thinking about knots, we can study surfaces that they bound into four manifolds and ask if those surfaces are smoothly equivalent or not smoothly equivalent. And we can also just study closed surfaces themselves, and we can even use them to show that manifolds somehow are homeomorphic, but not diffeomorphic. And the most interesting thing, and the only thing I'll actually draw anything other than an arrow for, from my perspective, is using them to understand cobordisms. So if you have a cobordism of a three manifold, so this is like M3, what does that mean? It means you thicken it up times I, and then you start attaching four-dimensional handles to it, right? A cobordism of three manifolds is four-dimensional. And you have some one handles, which are boring, not interesting. And then you have two handles, which are actually interesting, and they're attached along knots. So you can see that this very dimension accurate picture, this is attached along a knot in a three manifold. But on the other hand, one dimension up, if you have a cobordism of four manifolds, you would build that by thickening up to be five-dimensional and then attaching five-dimensional handles. And so as usual, one handles are boring, but now two handles are also boring because they're attached along circles, and circles in dimension 4 are much less interesting than circles in dimension 5. They're less than half-dimensional. Homotopy implies isotopy too. And then three handles are attached along surfaces, specifically two spheres, and these guys are actually interesting. So somehow knots in three manifolds and surfaces in four manifolds exactly describe the complex complexity of cobordisms. And to try to like show that a certain kind of cobordism is trivial, you would have to understand whether some family of surfaces is like trivial in some sense. So anyway, that's all very vague. But in order to actually do anything with knotted surfaces and four manifolds, you probably want to be able to like do some computations to like distinguish two knotted surfaces or like explicitly show that two of them are the same, like just be able to prove anything interesting about them. You need some way of actually describing them. Like I can't just tell you it's a knotted surface, I have to tell you which one, right? We're very good at describing knots in three manifolds. So here's, a very detailed picture of how you draw the trefoil. All you do is project your knot in, let's say, S3 to an equatorial two-sphere. Make sure that you'll just have a regular projection and then like break the double points to get a diagram. So we understand these really well. And, you don't even have to explain these. Like if you show them to an undergraduate, if you draw a trefoil, they know what you mean. Like they have depth perception. But it's way harder if you're talking about surfaces in dimension 4. You can do this exact same idea. We're just going to project everything one dimension down. So here's my picture of a two-sphere. It actually lives in S4, but I've projected it to the like S3 that we live in. So you should think that really there's like a whole annulus in here. So this two-sphere is intersecting itself in a circle right there. But just like for knot diagrams, we like break the undercrossing. I deleted like one of the sheets at this intersection to indicate that it is under, like deeper in the fourth dimension. Okay, so this really is a picture of a two-sphere that's knotted in S4. And in some sense, actually, like I would say objectively, this is the simplest non-trivial two-sphere. It even has a name. It's called the spun trefoil. You can see like it kind of looks like a trefoil. And just like the trefoil is the smallest knot, like this is somehow the smallest two-sphere. But this is the smallest one, and it's already like pretty bad. And its self-intersection set was particularly simple. Like all of the intersection points were just double points. They're very easy to break. In general, we'd have to consider like you have an immersed surface in dimension 3, it's probably going to have triple points like this. And it could even have these weird like cusp things, like the trace of a Reidemeister 1 move. So you have to understand like how to break those. And just in general, we should expect some like huge, like awful diagram. So this is kind of bad because like the nice thing about knot diagrams is they're so easy to use, right? Like it's very difficult to look at this whole thing or draw it all at once. So I would say the combinatorics is complicated. They're very hard to manipulate. And like, if it's this hard in S4, what are we going to do in an arbitrary four manifold? Which if I'm studying cobordisms, like I'm probably not just thinking about S4. I should mention that some people really do use these kind of diagrams. Scott Carter, Saito, what's Saito's first name? Masaki, maybe Saito? Carter and Saito have written a few books where they study surfaces, and these are like their favorite kinds of diagrams. But I would say that they're like uniquely good at using these. I find it very difficult. So instead, let's try to reduce the like combinatorial information that I'm having to convey to you by thinking about like, what is the minimum amount of information that I would have to give you in order to determine a whole surface? Like what's the smallest possible picture that I could draw? Okay. So here's a theorem, or I guess I wrote proposition because it's not like that hard to prove. Then some setting where we only have to give you a little bit of information and you can determine a whole surface. So if you're studying surfaces that are properly embedded in B4, so here's B4, then it's a fact that if I give an unlink in the boundary, so here's an unlink, then it bounds a unique collection of boundary parallel disks into B4 up to isotopy real boundary. So all I have to do is draw the boundary, some unlink, and tell you like, okay, now think about the boundary parallel disks it bounds, and that completely determines the surface. So to illustrate what I'm talking about, the boundary of B4 is S3. So here's the boundary, here's an unlink, 2 pictures of one unlink. And I'm going to draw 2 different sets of disks for this unlink. They're sort of the obvious one. But on the other hand, I could have like this disk sort of balloon around the other component and fill this in the normal way. And in S3, these sets of disks are not isotopic row boundary. Like to turn the right picture into the left picture, I would sort of need to like move this boundary to the right and like sort of pass it around the other component. I realize that I'm pointing right, and to you it probably is looking left, but you know what I mean. So, but we're not talking about S3, we're talking about isotopy in B4. And if we have a fourth dimension of freedom, then I can take this disk and just push it a little bit deeper into the interior of the 4-ball. So push in, and then I can move it to the left and get back to this picture without ever introducing intersections, because I've pushed it like into the fourth dimension. So this is actually like a fun proposition. If you get bored, like you can think about this instead, that's fine. But this is also going to be very useful. So let's say we have just a general surface, a closed surface in the 4 sphere. It's like, how determined is it from something? So this is my picture of a surface where I've like sort of indicated where some things are going to happen. This H is just like the 4-dimensional height function. So I should think that each of these cross sections are S3s. Maybe I should draw that in orange, but you know what I mean? Yeah, so this is an S3. So generically, they intersect my knot in a link. I've put my knot into like Morse position, but there are a finite number of cross sections that will be tangent to my surface, and like those are the Morse critical points, right? Okay, so what I've done here is I've preemptively isotoped my surface to pull the maxima all up to the top of the picture, so they're all there at the same height above everything else. And I've pulled the minima down. So they're all at the bottom of the picture below everything else. Okay, so now I've drawn these 2 S3s that cut off the minima and the maxima of my surface. So the point of this is like, this is an unlink inside of S3. This is also an unlink inside of S3. And if I look on either side of these orange 3 spheres, these are 2 4-balls that contain boundary parallel disks. So this is boundary parallel disks. Because these are all disks that just have like, it's just a maxima and nothing else. Like I could just push them down and have them be in the S3. I just drew them as curvy so that it would look Morse. And these are also boundary parallels, and as we call them, trivial disks. Okay, so what that means is sigma, my surface, is determined by exactly the middle region of this picture. Like I could just cut off the top and bottom and not lose any information. So that's already some progress, but we can still simplify more. The middle thing is like kind of curvy and bad and hard to describe explicitly. So maybe what we should do is flatten everything out. So instead of being Morse, I'm going to flatten all of these index 1 critical points that are floating around. So that, why did I erased this picture on purpose? Because I thought I'm just going to draw this. That'll be more convincing. So I get something like super non-generic, like this. What I've done is I've taken all of my index 1 critical points. So here's like a good round picture of what like actually an index 1 critical point looks like. And I flattened it so that its boundary is the same. But now all of the pieces of my surface are either horizontal or vertical with respect to height. So this is filled in like this. Okay, so if I were allowed to smooth the corners on the right, I would get back to the left picture. Okay, so when we do that, like we should interpret this picture as like, if we were to project everything down, I have this sort of bottom boundary, and then I have this horizontal region where I'm like sort of something bad is happening as I go up. And if we look at it, it's a square with two edges attached to the bottom and like two edges sort of going up. So if I projected it down, I would get this kind of picture. And we call this a band. A band just means a rectangle where like two of its opposite sides have boundary on a link. So this is a picture of a surface. With respect to height, I've drawn a few cross sections. My minima disks are completely determined by their boundary. My maximum disk is completely determined by its boundary. And I've flattened my index 1 critical point to just look like as I go up, I see this band. And as I pass the band, instead of seeing the two sides that are originally on my knot or link, I see the opposite two sides. So it looks like I've done surgery to my link along that band as I like pass it in time. Okay, so this is a picture of a two-sphere inside of S4. And instead of drawing all of this information, I think maybe I've convinced you that, in fact, I only need to draw this middle piece, which looks like an unlink, that's the boundary of the minima, with bands attached that encapsulate the index 1 critical points. So this is like a complete diagram. It totally determines the surface. I could draw something slightly more interesting. So again, I have, this is a movie of a surface where the minima are determined by their boundary. That's an unlink. At the top, even though I haven't drawn it as round, this is a picture of an unlink. So it does determine my maxima. There's two of them, but I only drew one line. And then I flattened my index 1 critical points. You know, my rectangles look weird, but they are still rectangles with two edges on, like two of the opposite edges on my link. And I see that as I pass them in height, I will just have the surgery on this link via these bands on the other side. Like I've deleted these sections of the boundary and replaced them with like the other two like long edges of the band. So this is a picture of a knotted surface. Again, it's a two-sphere. Yeah, inside of S4. But I don't have to draw the whole thing. I can just draw this section of it, which is this unlink, which is the boundary of the minima, plus some bands, which are my index 1 points. Okay. So what do you think about that so far? So I'll summarize the definition. A banded unlink is a pair of an unlink with bands attached to it, where the bands have to have the property that when I do surgery, I get an unlink again. Which isn't, if I just draw a random unlink and random bands attached to it, that's probably not true. So like this is like a special thing. And we've just observed that if I have a banded unlink, then I can produce a surface inside of S4, and vice versa. If I have a surface, I can produce a banded unlink. So the questions that like you should ask yourself are, how determined is this banded unlink given sigma? Like, can I produce a well-defined diagram of a surface? And if I have two surfaces that are isotopic, and from each of them I produce these band diagrams, how are those diagrams related? Like, is there a Reidemeister theorem? Right. Okay. So in order to answer either of these questions, it's helpful to like think about the Reidemeister theorem, which there are many proofs of. And in fact, if you've seen a proof, you probably saw something with like sticks or something. But I don't like that. So instead, I think it's helpful to think about, like, let's go down a dimension, like where do the Reidemeister moves come from? They come from bad projections of knots, like we're trying to build a diagram and something goes wrong. So where do Reidemeister moves come from? If I try to project a knot in S3 to an equatorial sphere, it might be that my projection is not smooth, it has a cusp. And if I like try to resolve that cusp, I'll have to make a choice of like how I do it. And the difference will be like whether or not I have a crossing or not. It could be that my projection has a point of tangency rather than like a transverse intersection. And then I'll have to like choose how I'm going to resolve that. Or it could be that my projection has a triple point, and I'll have to choose like how I'm going to, I only want double points when I build a knot projection. And I mean, maybe you should object that like worse things than this could happen. Like, why haven't I drawn quadruple points or like 3 tangencies or something? And like really what I've drawn here is like what I would call codimension 1 bad behavior. So generically, these things don't happen. But if I have a 1 parameter family of knots, like knot projections, then I do expect precisely these 3 things to happen a finite number of times. And I think, oh, I didn't even say this at the beginning, but like the paper that I'm supposed to talk about, the immersed surface paper, is something that I've been writing for like 2 years with Mark and Sungwon, and it's taking forever because it's full of tedious little details. And this is like, see, this is very easy to believe. You should immediately believe me, like these things are the only things that can happen. But to like actually convince you, I have to use like jet spaces and this like filtration on the space of circles embedded in 3 manifolds, and it's awful. But you don't have to know that. But these, like you can convince yourself maybe that these are the codimension 1 things. So these are the codimension 1 behaviors. And if you like look at them, they sort of obviously look like the Reidemeister moves, right? Like that's 1, 2, and 3. Okay, so we can do the same thing for surfaces. Like we want to understand how well are diagrams defined. Well, think about when you do a projection, like at what point did we have to make a choice? Like when was the projection bad? When we are getting our banded unlink? And then like those things will also tell us like when we do an isotopy, like have a 1 parameter family, we're going to have to understand those finite times when something bad happens, and they will contribute moves. Okay, so what are the codimension 1 behaviors in dimension 4? Well, I did need my surface to be Morse. I just said, like, take it to be Morse, and generically I can, but in a 1 parameter family, I can't. And if my surface didn't start off as Morse, I would have had to make a choice on how to make it Morse. And the bad thing that can happen is that I have a degeneracy, like where it's the start or end, like it's the start of a birth of a 0-1 or 1-2 pair of canceling critical points. And so if I look at what happens, like, depending on how I resolve this critical point, well, on the left, I've drawn a surface where there's no critical points, it's just vertical. So I think you can believe that, like, I'm just supposed to draw the boundary of the minima, like, the surface is just vertical. It's just going to project to, like, a link. And on the right, I've drawn something that's round. So, like, really, maybe I should flatten it so you can see better what this is. I have something with a maxima. Can I draw this? Maybe I can. It comes up. It's supposed to like join over here. Okay, this was like not a very convincing picture, was it? Let's draw it like this picture. Blah, blah, blah. Okay, so what is this like thing that I've drawn a band diagram for? It's a surface where it has one index 1 point corresponding to the band. And when I do the band surgery, I see that I've made a little like unknot component that contributes 1 extra maximum. So here I've sort of drawn like a rectangular picture of the surface. And this is just the flattened version of this guy. I've like flattened all of my like Morse critical points. So depending on how I resolve this like non-Morse point, my diagram will change by adding a little trivial band or not. And then there's the upside down picture. Somehow it's like psychologically easier to draw this one flattened. I have an extra minima, which I flattened to be like a whole disk whose boundary is an unlink, an unknot. And then it attaches by some like flat thing to my surface. And then I have the rest of my surface coming up. Okay, so this is the like flat version of this. And this corresponds to having 1 index 1 critical point, which looks like a little band that just joins my surface to the new minimum. Okay, the other 2 moves are like somehow easier, even though they're more complicated. The other thing that I did was I had to actually flatten my surface. And I'm just talking about that, like that's a well-defined thing, but it's not. Like if I have a surface that's in Morse position, to flatten it, what I mean is like I'm choosing a 1 skeleton of my surface that I'm going to like flatten and become the bands. Like I like to think of this as like I'm looking at this induced Morse function on my surface. I'm looking at like the index one critical points on that, and there are flow lines. And there's something about like when is there a flow line from an index 1 point to an index 1 point? But I think that's confusing in a talk. So I will say that there is like a Morse theory way of saying like what is the problem, the codimension one thing that actually would convince somebody that it is a codimension one thing. But here I've drawn something that kind of looks like a monkey saddle, and two different ways of flattening it. Like I could either choose to have my one skeleton sort of like connect these two guys, or to connect these two guys. And like depending on like which one I choose, if I flatten it, I'll get like two different choices of bands, which just look like those arcs flattened out. These differ by like sliding, like really to get from top to bottom, I should think I'm taking this band and like, oh, I already have an arrow, and then sliding it over this one on the left. So I'll get this picture. So the point here is just that like, if I have two one skeletons of a surface, I can turn one into the other by like just sliding the edges around. Like I've fixed the index 0 points, but they have different edges. Like that's all I have to let myself do. So I put my surface in Morse position, I flattened it out, and then the only other thing I did was I projected all of those bands to one height so that I would get one diagram that was an unlink with all of the bands in it. So then like the bad thing that could happen, so this is a picture of 4 dimensions, like each of these pictures is really an S3. It contains a link. And right now the bands are all in different heights. So there's also some bands. And these are 2 bands, which are flattened index 1 points of my surface, which are of course disjoint from each other, but they happen to be in the same position in like 3-dimensional space. It's just that this one is like strictly above in the 4th dimension. So even though they're disjoint, their projections look like they intersect. So it's kind of like having like, I don't know, a tangency or something like I don't know, some kind of self-intersection like for knots. But anyway, I don't want this to happen. So I'll have to choose to take this top band and move it either to the left or to the right to make the projections disjoint. And if I do that, I'll get diagrams that differ by this move. And so again, in terms of Morse theory, like somehow I'm saying there's a flow line between 2 critical points on the boundary of the complement or something, but whatever. Okay, but this was really like the whole step, the whole procedure of getting the diagram. I put my surface in Morse position, I flattened it, and then I projected everything down. And then I had a diagram, that was it. So this is the theorem, Swenton, and then Kierton and Curlin added some like details, like more rigorous, I guess, where they showed that if you have, well, first of all, if you have a surface in S4, its diagram is well defined up to these moves. And in particular, if you have 2 isotopic surfaces, then their diagrams differ by exactly these moves, which like correspond to an isotopy. Like somehow I could think of these moves as really describing an isotopy. Okay, how do you feel about this so far? Okay, so this was dealing with the complexity. I mean, like unlinks with bands attached, I think are not that much worse than just links in S3. So now we can draw surfaces in dimension 4 and like really move them around. Like I feel very comfortable moving things in dimension 3. It's like easy to do these moves. So that's much better than that like blue immersed 2 sphere that I'd broken and like that looked bad. I do have a t-shirt with that on it, so that's cool. But now I want to deal with the other thing that I brought up, where like actually I care about other 4 manifolds, because the reason I'm interested in surfaces is not exactly just like as knots, like a knot theory. It's because I want to describe like cobordisms and find exotic behavior, and S4 is kind of bad. So I want to understand an arbitrary 4 manifold. So I need to think about what information determines the surface. So here's our first proposition. It's the same as our previous one, which gives at least one setting in which a surface is determined by something. So this is just like our claim before about if we have an unlink, it bounds a unique collection of boundary parallel disks into B4 up to isotopy real boundary. Now I'm telling you the same thing is true in a boundary sum of S1 cross B3s. So you also called a 4-dimensional one handle body. As if I just draw an unlink in the boundary, then there's a unique collection of boundary parallel disks. This is actually not harder to prove than the previous one, but like that's not obvious. But in particular, like if you're familiar with 4 manifolds, then I think that you should be very happy to see boundary sum of S1 cross B3s, given that I'm pulling things up and down and there's Morse functions, these things show up all the time. So here's a reminder, how do you draw a 4 manifold X4? I've drawn this like little picture for myself, so I remember which one to draw. That's very informative. So again, I'm going to fix a Morse function, H, and I'm going to make sure it just has one index 0 point and one index 4 point, blah, blah, blah. Great. And then I'm going to make it be self-indexing. So all of my index 1, 2, and 3 critical points will be at the appropriate height. So something like this. And in particular, if we look at, let's say everything below height 3/2, this is a manifold which has a Morse function with only an index 0 point and some index 1 points. This is a boundary sum of S1 cross B3s. And similarly, if we look above height 5/2, so it has index 3 and 4 points, but it's also upside down, then this is also a boundary sum of S1 cross B3s. So if I have a surface in a 4 manifold, I'm going to make it be Morse with respect to H, and I'm going to pull all of the maxima up and the minima down, just like before. This is fine. So all of the maxima are above height 5/2, and all of the minima are below height 3/2. And that way, inside of these S1 cross B3s, my surface just intersects them in boundary parallel disks. Okay, so that's not how you write that. Boundary parallel disks, because they're just disks with one critical point each, and like you have to maybe think about that for a little while. But I claim that that implies that I could just make them be flat and isotope them the boundary. Like if I flatten my surface, like I'm gonna have to do, like that's what they look like. Okay. So my lemma from before says that those disks are just determined by their boundaries. So just like in the S4 case, our surface is somehow determined by this like middle region, like the boundaries of the minima, the boundaries of the maxima, these index 1 points, index 1, and the index 2 points of my ambient Morse function, which makes sense because like in dimension 4, those are the bad ones. Do I have a picture of that? Oh, I thought I would draw a picture of that. Oh, I even defined a Kirby diagram, but I feel like you guys know what that is. Okay, so here's my surface. So sigma is determined by this middle part. And again, like this is better, but we can make this even more simple by like taking our sort of like round looking surface and perturbing it to like not be Morse anymore, to just be like very degenerate, like always like horizontal and vertical. So I'll flatten all of my like index 1 points, just like before, they turn into bands. Become bands. So now my surface is determined by the boundary of the minimum disks, these flat bands, which are my index 1 points, and the index 2 points of the ambient Morse function, which I'm going to describe by like a Kirby diagram, which sometimes, like if I'm giving a talk in a topology seminar, I do define, but I'm not going to, so I hope that that is cool. So a banded unlinked diagram is a triple where I have to tell you a Kirby diagram of my ambient 4 manifold, and I have to give you an unlink, which is an unlink in the Kirby diagram. Oh, I guess I should mention by Kirby diagram, I mean a framed link in a connect sum of S2 cross S1s. So there's no dotted circles if you would have worried about that. But if you didn't, that's fine. So L is an unlink. And these bands should be attached to L. And now the condition is that if I surge L along B and I do the like two handle surgeries, I should get an unlink. So I drew an example of that because that's complicated. So here's my Kirby diagram. I have my like framed link here. It specifies a two handle. I don't have any one handles. So this is CP2. L is very obviously an unlink, an unknot, right? And if I do the band surgery, so if I do the surgeries, then L surgered along the band becomes this thing that looks like a hop link. But I also have to do this surgery corresponding to the two handle. And so if I blow down this one, it'll actually undo the twist. And so this is actually a picture of a two component unlink inside of S3. So this is an unlink. So that means that this is specifying a surface. It has one minima, one index, one point, and two maxima. So this is a picture of a two sphere inside of CP2. If you thought about it, I think that you could convince yourself it's null homologous. And if you're comfortable with Kirby calculus, I think you could convince yourself this is the unknotted two sphere. This is, well, first of all, a diagram of S2 cross S2 on the right. Again, the circle that I've drawn is an unknot. I'm ignoring the handles. The minima is like below all of the handles. I just have this disk. So this is like the minimum. There aren't any bands, but when I do the surgeries corresponding to the two handle circles, again, the circle is an unknot, but sort of in a different way. It bounds a disk that's like capped off by a core of this two handle. So this is like the maxima. So this is a picture of a two sphere with one minimum and one maximum. And in fact, like if we're sort of comfortable with Kirby calculus, I think you could convince yourself that this is like S2 cross point or something. But you don't have to convince yourself that, it's fine. Okay, but this is how you draw a surface. To what extent are these diagrams well defined? And again, like, what does it mean? Like if I have surfaces are isotopic, like how are their diagrams related? And it's very similar to the S4 case. Like we have to think about those, like what are the bad things that could happen as I'm trying to produce a diagram? When did I have to make a choice? Codimension 1 behaviors. And this includes like everything that could have happened before. So now the only difference is that I have these like two handles in my manifold that are sort of in the way of everything. Two handles always in the way. And in particular, what I mean by that is I had to project my bands down. I wrote so small. I had to project my bands like all into this like Kirby diagram, but they might have been stuck like above a two handle. So I drew an ascending manifold, but like I just mean like the two handles in the way. I would try to go down, it would get stuck on the index 2 point. And if that's the case, I'll have to choose to push the band to one side. And the difference is sliding a band over a two handle in the Kirby diagram. The other bad thing that could happen is I try to build my diagram, and instead of the band like sort of lying in the Kirby diagram, it actually intersects the attaching circle of a two handle. Like it's in, I would say it's in the descending manifold of the index 2 point. And then I will also have to choose a direction to like push the band to resolve that. And I get something that looks a lot like my band swim before. So Mark and someone and I 2 years ago, I only talked about the embedded case, but that's fine. Mark and someone and I showed that, in fact, any surface in a 4 manifold, you fix a Kirby diagram, then like you can produce a band diagram, which is well defined up to these moves. You can also do Kirby moves if you want, but if you want to talk about isotopy, you have to be very careful, because once you start doing like two handle slides, like that's not isotopy, that's diffeomorphism. But if we fix a Kirby diagram, like a parametrization of our 4 manifold, then we can also talk about isotopy. And so then in addition, like two surfaces that are isotopic give band diagrams that are related by these moves as well. Okay, so this is like a Reidemeister theorem. You can see that like things are starting to get bigger. We have more moves. The thing that I've been working on forever that I wanted to tell you about was immersed surfaces. So I'll give you like a little bit of that. Oh, here's a corollary. We don't care about this. Bridge trisections. But we might be interested in immersed surfaces for me because you need to understand immersed surfaces in order to understand certain invariants of surfaces. So there's interesting family of invariants studied by like Friedman and Quinn. I never know like when it's just him or when it's like the both of them. That are defined explicitly using homotopies, where we have to like build a homotopy and then like see how it intersects itself. And good luck doing that. So we have to actually like draw things. And so what is codimension 1 behavior? Like, what do I mean by that more, I guess, rigorously? What I mean is that if we look at an index 1 critical point, like, why is it so bad? Like, by that, I mean these index 1 points in our surfaces that flattened into bands, like somehow they were giving all of the complexity of the moves or like all of the complexity of the surface. The point is that if we look in the complement of the surface, so here in pink, I've drawn like a neighborhood of my surface. Then if we look at everything above and everything below an index 1 critical point, both of those things are 2-dimensional. So here I said ascending manifold is 2-dimensional. That means like I have this index 1 point in my surface, and I've sort of illustrated like this arc, which lies directly above that point. And so does this arc. And like there's a whole family of them. So it's 2-dimensional. And also, if I look at the collection of points below my index 1 point, it's also 2-dimensional. And the reason this is bad is that well, I'm in dimension 4 and 2-dimensional things intersect in points. So that means it's very easy and possible for like index 1 points to lie above or below each other. An index 2 point of an ambient Morse function has these exact same properties. A 2 handle has like an ascending and descending manifold that are both 2-dimensional. And you probably believe that those contain like all the complexity of a 4 manifold. So somehow all of the complexity of a surface is in those 2 handles and these index 1 points, and they like look exactly the same from the point of view of a Morse function. And if I have self-intersections, it's actually the exact same thing. This picture is a little bit harder to understand maybe. But what I've drawn here in black is a picture of what an intersection of a surface looks like. Like I have these 2 arcs that are disjoint from each other, and as I go forward in time, they intersect like first tangent, and then there's like a crossing change. So this is a picture of a transverse intersection in dimension 4. And I've just illustrated, like, I've drawn a whole neighborhood of this thing in pink, and all of the points below and all of the points above, again, are 2-dimensional. So somehow from the point of view of Morse theory, an intersection point and an index 1 point and 2 handles are all like exactly the same and like contain all the complexity. So I'm not gonna like go through the like actual moves, but I will show you the theorem because I think it's very funny. So Mark and Sungwon and I showed that there exist diagrams of immersed surfaces where I draw singular links. The singularities like mean the intersection points with bands attached, and they're related by these moves. So the problem is that like once you add intersections, it's like before we had band over band, and it could be in space or in surface, and then we had band above 2 handle and band below 2 handle. And now we have like intersection, above band, below band, above 2 handle, below 2 handle, above band and space, below band and space, above each other, below each other. You know, those last 2 were the same thing. So you get like a move for each of those like different things that can happen. So this looks super awful. But actually, like once you get kind of good at it, it's just a principle of like you have these 3 things and they can go through each other. Like you don't have to break it up into cases. It's just sort of, you know, you don't do Reidemeister moves one at a time. And we can understand regular homotopy too. We don't care about those. So here's my like sample use, which to define some invariants of a pair of homotopic 2 spheres. I sort of mentioned that we might want to construct homotopies with different properties. So this is an invariant that you should not know what this means. Actually, I'd be impressed if you guess what KM means, Mr. Jason. But this is a pair of two spheres, has associated to it an invariant called the Kerber-Milnor invariant, which can obstruct isotopy and concordance and is very difficult to define. In order to define this invariant, you have to produce a homotopy between your two spheres that at the very least has this weird property that all of the self-intersections have disconnected preimages. So what do I mean by this? A homotopy between two spheres, S0 and S1, is an immersed S2 cross I between them. I mean, it's like a special immersed 2 cross I, but I think that we can agree that like this is what a homotopy is inside of like 4 manifold cross I. And when I have a 3 manifold immersed in a 5 manifold, I expect double points of intersection. It's like, you know, half dimensional plus 1/2. So I should have these like circles, and they're double points. So each of those circles is double covered by its pre-image, which means one of two things, because the circle has 2 different covers, double covers, right? It could be that it's covered by 2 disjoint circles in S1 cross S2, or it could be that it's covered by like, wow, I'm really bad at this color coding, 1 twice as long circle inside of S2 cross I. Okay, and so I'm telling you, like, at the very least, to define this invariant, I don't want this to happen. And then like that's just step 1. Step 2 is like I actually am gonna have to like really understand what these are. It's really bad. And so I'm writing this paper eventually with Michael Klug. We're both, I don't know, we're both like playing phone tag or something, where we have to like really build these homotopies explicitly. So I drew this picture, which I also think is funny. This is an illustration of like, you don't really know what these diagrams are, but I'm just telling you that like each of these describes an immersed surface. These bands describe the index 1 points. These like weird things describe the self-intersections. And I have this like long list of moves that I can use to describe isotopy and homotopy. So here I've really drawn a homotopy from like this like little piece of an unknotted surface to itself, where I can very explicitly understand the self-intersection set. So in particular, like if I look at like this sheet at a self-intersection, sort of like the part of the pre-image that goes up and right, I can follow it through in all of these pictures, blah, blah, blah. What am I doing here? It's like this, something. And something weird will happen where it will sort of become the other sheet by the time that I like finish the homotopy. So I've actually constructed something whose self-intersection set is like 1 circle. But if I try to like trace it through, if I like start in 1 sheet, by the time I go around once, I'm gonna come back in the other sheet. So it actually doesn't look like this picture I've drawn of like 2 disjoint things. It has like 1 connected pre-image. This is very like, I think, confusing since I didn't actually define these diagrams, but I do want to convince you that there is a point to all of this, even though it's like a big pain. I'm getting really good at this. This is like my picture of this Whitney disc and like how I actually produced this. But yeah, I think they're really fun. So I guess I'm gonna stop there.
Okay, let's thank Maggie then.
Did the embedded case very thoroughly, 30 seconds of the immersed case, good ratio.
Okay, are there any questions for Maggie?